Well, here we are. We're finally getting to the second half of the title you're seeing on the screen, graphs. Their graphs, the function graphs. We haven't talked about how to graph functions yet, but we're all set. We've got all the parts we need. So the next topic will be visualizing function graphs of x, f of x pairs. So let's talk about that. Visualizing functions. First of all, let me go ahead and recall what we know about functions. We thought of them in two ways. One is correspondence, one is a machine. So in tiny pictures here to kind of remind you, this was the correspondence definition. Correspondence, right, where points from the domain of f went to the range of f, and they were such that 2 points here may go to the same place as this one here and this one here seem to do, or not. And that was a correspondence definition. Or we also saw these functions as machines, where the domain elements, the x elements, the input elements, went into the function f and came out as f of x. Now in all of these, what do we really need to know the function? Well, we like to know the actual machine of the function or the correspondence somehow. But as I said before, if we cover up the center part here, and all we knew were the points on the left and their corresponding matches on the right, in each case, the x and the f of x over there, the points here and the points there, then we would know, if we knew that for everything in the domain, we would know everything about the function. So let's follow that train of thought. In each definition of function, big topic of the time, in each definition of function, if we know, so here's my little if we know all the ordered pairs. Now ordered pairs, remember, are pairs in which it matters which number goes first. The pairs that look like what? Well, input element is the first member of the pair. Output element is the second member of the pair. Or if you don't like that, domain element and range element. Or to put it in notation, x and f of x. Or to give you an example, if the function were f of x equal x squared, then we could say 0, 0, because 0, domain element, when squared is equal to 0. 1/2, when squared is 1/4. -2, when squared is 4. -10, when squared is 100, etc. All infinite number of such pairs, ... Remember what I was saying there, continue back here. If each definition of function, if we know all the ordered pairs, whether you think of them as input, output, domain, range, x, f of x, or in this case, an example of of a particular function, then, here comes the then that goes with that previous if, then we know the entire function. It suffices to have all of those pairs, because that tells us how everything works. But wait. But wait. Pairs. We know how to graph pairs. We can graph pairs. We know that from the previous work we've done. We can graph pairs, so we can, therefore, visualize, or if you like the other way, graph functions. We can now visualize them by graphing all those ordered pairs, because we know, if we know all of the ordered pairs, we know the entire function. So let's put this down. Definition. Just combining everything we've just said. to graph a function, say f, which takes x to f of x, just plot all the ordered pairs. Remember, the order matters because we want the domain elements to stay on the left and the range elements to stay on the right. All the ordered pairs, x, comma, f of x. We will therefore treat f of x as the y-coordinate point, which is the reason why we previously could write y equals f of x. That's why that became common. So we will plot all the points x, f of x, and that will give us a graph of the function. This will give us a visualization of the function, a way of looking at the function that does not come out from just looking at the correspondence or the machine. So this is really a wonderful aspect. Let's notice something here. Let's see, a little derivation we're going to develop here. Notice, by definition of function, there was something else that occurred in the definition of function. It wasn't just a machine or a correspondence, but it was a correspondence in a machine where each domain element went to a unique range element. So by definition, each x goes to use one of our colloquial phrases, we could say is associated with, a unique f of x. Although, just to remind you, although several x's can go to the same f of x. Okay, how does this translate now into graphical imagery? This translates here into the following kind of statement. I could say that if I had points x1, y1, x2, y1, excuse me, x3, y1, the same y in each case, where x1, x2, and x3 not all equal, this is okay, because we have three different points going to the same y value. There's no problem with that. The picture would be three different points all going to the same y value. That's acceptable in the definition of a function. But having even as much as two, x1 comma y1 and x1 comma y2, where y1 is not equal to y2, this is not allowed. Okay, because this is a picture where you have x1 going to y1 and simultaneously going to y2, and we know that both of our definitions make that a meaningless statement because we want our x to be unambiguous in where it goes, whether it's a machine or a correspondence. Okay, I'm actually getting somewhere here. These kinds of point situations are okay. This is not okay. Now notice what we have here. 2 points with the same x-coordinate. So we can write down the following. So 2 points with the same x-coordinate but different y-coordinates are not allowed. But what kind of points are those? Let's see. If this is my x and y system here, and say here is the point x1, and I'm told that x1, y1, x1, y2, this is the situation that is not allowed. Well, x1, y1, x1, y2, where do they live? This might be x1, y1, this might be x1, y2. In other words, this is a vertical line. And everything that we've said says that you cannot have, in a function, 2 points which lie on a vertical line. Well, putting that all together, we now have a theorem that allows us to look at the graph of a function, or a graph, let's say, and tell whether it's the graph of a function or not. So, we have a theorem. And this theorem might be called the vertical line test. I told you we'd see theorems in this course, and we certainly are. The vertical line test. And here's how it goes. This is a bidirectional theorem. It's an if and only if. Double arrow theorem. A set of points in the xy plane is the graph of a function. Okay, that's what we want to be able to tell, is the graph of a function. Okay, let me box that in. That's one side of the double implication. That is going to be true if and only if, double arrows, any vertical line at all in the plane intersects the graph that we're looking at here, the graph at most once. So let me read that again. The set of points in the xy plane is the graph of a function, it's a particular kind of graph, if and only if, or double implication, any vertical line intersects that graph at most once. Because if it intersects twice, then it violates the definition of a function as we saw a moment ago. So now you have a wonderful test. By looking at a picture, you can tell immediately whether you have the graph of a function. So let me give you a couple of pictures here. Example. Here's a picture, and let me draw another one. Example. Here's another picture. Now, is either one of these the graph of a function? Well, based on only what you see, okay, not knowing what the function is, based only on the fact that this is the x and y axes in each case, and these are the pictures, which of these is a function? Well, based on that, you can see from the first one that if I were to draw any vertical line anywhere, it's only going to strike once. Possibly not at all if I go out far enough to one side or the other. But if it does strike, it only strikes once. So this is, yes, a function. And there I'm starting to abbreviate function already, FCN. But this one, however, is not a function. It is a familiar curve. It's a circle. And you might say, well, shouldn't all these familiar curves be functions? Well, no, not necessarily. This is not the graph of a function, because here's a vertical line. And it strikes the curve once, twice, and that is not allowed. Now, there are some vertical lines that only strike once, like the one that's tangent to this end. And there are some vertical lines that miss it altogether. But that's not the point. Remember what the theorem says. It says all vertical lines. If there's any vertical line that strikes it more than once, it's not a function. So this is not a function. Okay? So now you have a test. Strictly visual. Okay. Let's spend a little time examining the graphs of some generic functions. Later on here in this unit, we're going to talk a lot more about functions, but let's just talk about some generic things right now. This is a situation where, given a function's graph, what can you say about the function? Let me draw the graph of a function here, and we'll talk about it. And I wanted to draw this so you can watch what I'm doing here. You go out 6 units on the x-axis, and then 1, 2, 3, 4, 5 units on the y. So that's the y-axis. This is the x. The function will have a point here, which I will mark, another point here, so you'll be able to follow where I am. So there's part of the graph of this function. This is the point 6, 1 here. This is the point 3, 4, so this is 3 here. And this is the point 0, 4. And then let's go 6 in the negative. 1, 2, 3, 4, 5, 6 in the negative. direction on the x-axis. There's another point that I'm going to want to label. That'll be the point minus 2, 0, minus 2. And then we'll go below in the y, minus 2, minus 1. And let me complete this picture. This point here is the point minus 4, minus 2. And finally, this point over here is minus 6, 0. And this is the graph of the function. It starts over here on the left, it ends over here on the right. Okay, and I think I've labeled everything. Now what I want to do is answer a few questions about this function. I won't actually write down the questions, but I'll bring the picture back as we do this. First thing I want to do is compute some values of the function. Now see, here's the graph. This is the graph of f, or f of x, the range elements. Okay, that'll be the graph of that. Now I don't have a formula for this. I don't know anything other than the picture. It is a graph of a function, though, by the vertical line test. You can see that because no vertical line is going to strike more than once. Suppose I want to compute f of minus 6, f of minus 4, f of 0, and say f of 6. Well, f of minus 6. I'm asking, when I put a domain element 6 in, what range element comes out? Well, look in the picture. When I put the domain element minus 6 in, what range element comes out? Well, look at these ordered pairs. There's the domain element paired with its range element. So all I really have to do is look at the domain element and then write down the range element. 0 is f of minus 6. So it's 0. Then I want to know about minus 4. Minus 4, minus 2, because minus 2 is the range element associated with minus 4. So minus 2. What about f of 0? Here's 0, 0 to 4. 0 is the domain element, 4 is the range element. So it's 4. How about 6? 6 to 1. 6 is the domain, 1 is the range. So I've answered this question pretty easily from the picture. What if I want to know the domain of the function? Well, the domain of functions is always going to live along the x-axis because the domain, remember, consists of the x's. The range correspondingly will live along the y-axis because it consists of y's, or f of x's. So where do we start and where do we end? Well, we start at minus 6 and we go to 6. And both are included. So this is simply one interval from minus 6 to 6. And in this particular case, the range of f is equally easy to find. We just have to figure out how low it goes and how high it goes. It goes this low, which is minus 2, and it goes this high, which is 4. So the range is minus 2 to 4. Now usually, as I said, the range is not as easy to find. In this case, because it's a nice picture, it's pretty easy to see. And I suppose we could do some other things, but I'm going to just stop right there on that example because I want to now look at an example with a little more juice to it. This is the first of what you might call real-world problem or word problem. And it fits here, so I'll go ahead and look at it. Here's the situation. We have a page that 8.5 inches by 11 inches, just the size of a normal sheet of paper. It has a border of width x, same width, uniform all the way around. And that border surrounding printed matter. So here's the kind of picture you'd have. 8.5 by 11, sort of like that, say. So this would be 11 inches. That's what these double quotes mean, by the way. They mean inches. 11 inches, and across the top, 8.5 inches. Instead of the 8.5, I'll write 8.5. And then what we've got in here is printed matter separated from the edge by a border that's always the same. So in here, there's some printed matter. This is my way of indicating printed matter. There's a long sentence, okay? printed matter. And the border is the same all the way around. X there, X this direction, and X in the other two. So we have this uniform border. Now we can ask a few basic questions. And I'll have to bring that picture back in a moment. A. Let us write down a function that represents the area of the printed matter. Okay? So the area of printed matter. And we want to have that area in here, this region in here, represented using the variable x. So I need, because this area in here is clearly a rectangle, I need to find the width and the height of the rectangle. But if you look at this picture, you see that the paper is 11 inches long. You've taken away a border of with h here, x there, and another border length of with x down here. So you have 11 minus these two. And that should give you, here's the printed matter, it should give you a height of 11 minus 2x. Well, once you see how that works, you can guess what the bottom one has to be. 8.5 across, minus x here, and minus another x here. So it's also minus 2x. So it's 8.5 minus 2x. And so the area, which will be a function of x, is the height times the width, or 11 minus 2x times 8.5 minus 2x. So there you have the function representing the area of the printed matter. And of course this is in, if you care about the units, this is in inches squared. And that's a function representing what you wanted it to represent. Let's go ahead and examine a little something else. What would be the domain of this function? Well, I have to ask myself what x's are allowable in here. So I have to go back and look at the picture. So I ask myself, how small could x be? How small could the border be? Well, theoretically, as far as the mathematics goes, the border with this x represents a length. It could be as small as 0. There is no border in that case. So the domain of A could be, let's see, the set of all the x's in the real numbers such that x is greater than or equal to 0. And the reason for that inequality is that it's a length. And in a physical problem like this, length can't ever be negative. But it could be 0. And then we have to ask ourselves, how big can the border get? Well, what you want to do is imagine the border squeezing in from both sides and from the top and bottom at the same time. Now, squeezing from both sides, there is less room. You only have 8.5 inches to work with. So you will smash together in the middle before the ones from the top and bottom come together. At what point do the two x's coming in meet? Well, they meet at exactly the halfway point. And what's halfway for 8.5? Well, that's 8.5. That would be 4.25. So x could get that big, but no bigger. Because once it reaches the middle, from both sides, there's no more area left, is there? So 4.25, putting it in decimal form, is the maximum that the x's can attain. So there's the domain. Great, we're on a roll here. Now we only want to do a graph. So part C, let's go ahead and graph A of x. Now if I were you, I'd get out my graphing calculator and do it there. That's how I did it. Here's the window I used. Remember how windows are written? You have the x values here and the y values here. Well, you know what they are? This is the domain, and this is the range of your function. And you can make either one of those bigger if you want, but that's all you need. The domain we've just figured out is 0 and 4.25. The range you can figure out also. The smallest the area could ever be would be 0, of course. And the biggest, if you make a little effort, you'll see is 93.5. Now, I will let you check that out on your own. That's, of course, the case when you have 0 as a border. Then the range is the entire piece of paper. So 93.5 is 11 times 8.5. There's your big hint. Okay, with that, putting it in your graphing calculator, you're going to get a picture that looks roughly like this. There are the axes, and the graph of a of x looks exactly like this. It touches there, touches there. That's a of x. This is 93.5 up here, 0 here, 0 here, and 4.25 here. So there's the graph of the area function, and then you can ask various questions, even with your graphing calculator and the knowledge you have now. For example, between 0 and 93.5 square inches, you could say, when does it reach 70 square inches? 70 inches squared. Well, that's going to happen right here if you go over to the curve. And if you use trace, the trace key or button on your calculator, then you can trace up there until the y value is 70, approximately, and you'll find that the x value is about 0.64. So when the border is 0.64 inches, the amount of area for printed matter is 70 inches. So if you're a person who wants to get the most printed matter on there and still have a border, you know exactly how to go about doing that. Well, I think that's a wonderful example. And on that note, we'll stop and come back and start talking about functions in general. More of the features that you can use to graph them more efficiently. Now that we know the basics of how to graph a function, we're going to look at some of the more interesting properties that functions can have and how we can visualize them and how we can tell from the function formula whether or not the graph has those properties. For example, we're going to look at increasing and decreasing functions. Now those sound like very visual ideas, and in fact they are. So let's go ahead and look at that. Increasing functions. The graphical idea is the very first thing I want to look at. And with increasing functions, I'm going to draw a little arrow here to indicate we're talking about going up to the right. Now remember, when we do increasing, we're talking about, in our graphical system, this kind of picture, okay? We go to the right on the x-axis, or we go up in the y direction. So these are the two directions that are primary for us. I'll bring this back as I need it. Okay, the graphical idea is as follows. Let me go ahead and draw in a couple of standard axes here, the x and the y axis, and then let me draw a function that we will consider to be an increasing function. Oh, something like that. Now, increasing has to be defined with respect to a particular direction. That's why I have this picture. Our direction is going to the right. So from our point of view, if you're walking from left to right, up, as you go from left to right, will be considered increasing. Because, of course, if we go the other direction, this would be thought of as decreasing. So for us, moving from left to right, this is increasing. This will be an increasing function. Now, how are we going to tell from the picture whether or not it's increasing? Well, here's one way to do it. Take what I just said and let's write down some symbols for that. Suppose I start out at position x1 here, and I move over to position x2. I'm moving from left to right, as I said. Now notice that x2 is bigger than x1. I'll just go ahead and write that in. Now let's see what happens when we go up to the curve here. So dot my way up there to the curve, and the same thing over here. Now what are these points? Well, first of all, I need to label what the curve is. Let's just give it a generic name. Let's say this is the function y equals f of x, using the notation we've developed so far. All right, well that makes this point, since the x value is x1, the point x1 comma f of x1. And this point, since the x value is x2, x2 f of x2. In other words, for the first point, the height, this distance right here, is f of x1. So if I mark it over here on the y-axis, this is f of x1. Likewise, for f of x2, this height is its height. And if I mark it over on the y-axis, I have f of x2 here. And since that's above f of x1, the inequality goes that way. The number on top is larger than the number on the bottom. This is where we have a moment of aha. Because if we move from left to right down here, from x1 to a greater number x2, and the function's increasing, it looks like the same property holds for f of x1 and f of x2. F of x1 is less than f of x2. It looks like I might possibly have a test now that doesn't involve drawing the picture. I can do it just by looking at the function. So, with that in mind, let's go ahead and write down an algebraic definition for increasing. So this is definition, this is algebraic as opposed to the graphical one we just looked at. Algebraic, all right. A function, already I've started abbreviating function as you know. A function f is increasing, I underlined the in there, so that's increasing, on some interval, because that's all we usually look at or we can see in a graph, on some interval, we'll just call it I to be generic. If, and here is the big condition, if for any x1, x2 in the interval, now that's the x1 and x2 that we walked from x1 to x2 on the x-axis, if for any x1, x2 and I, we have this situation, x1 less than x2, that means we're walking from left to right, implies that f of x1 is also less than f of x2. And how do you remember this? Well, you recall the picture is what you do. And if you recall the picture, it's very hard to ever get this wrong. Okay, let me bring the picture back. In the picture, if you go from x1 to x2 and the function's increasing, then the first y value f of x1 must be less than the second y value f of x2. That's what increasing means. It means you get higher as you go to the right. And that's all that I've written down here in the algebraic definition. As you go from left to right, the y values correspond. Okay, now I'm making a big deal of this because we're about to talk about decreasing, and in decreasing there's going to be something slightly different. So the idea here is to recall the picture, and if you do that, you'll be in good shape. So let me draw a couple of more pictures of increasing functions just to add to your collection of pictures in your mind. This is an increasing function. Now you might have some objection to it bending down, but it's not going to bend down so that it actually decreases. It just has a concavity that's downward, but it still is increasing. Here's another one. There's another increasing function. X and y axes. It is going up as we go to the right. It fits your notion of what increasing ought to be. Okay, with those both in mind, let's go ahead and look at decreasing. We've got the ideas already set up, so all we have to do is modify them slightly to come up with an idea of what a decreasing function would look like. So decreasing functions, and again, I'll put my little arrow here, right? That means going down. Okay, decreasing function is going down as you move from left to right. The graphical idea is similar. I will draw a pair of axes here, x and y, and I'll draw a function. There's a function that's going down, okay, as we move from left to right. And I think you know what I'm going to do. I'm going to perform the same procedure I did before. Suppose I have a position x1 and I move to the right to a position x2. Again, x2 is bigger than x1 because I'm moving from left to right. Now let me go up to the curve, one point there and another point here. The first one has coordinates x1. Well, I better label the curve again. This is y equals f of x, say, just to be generic. So this will be the point x1, f of x1, and this point will be the point x2, f of x2. So that means for the first point, the height is f of x1. I go over to the y-axis and I mark f of x1 for the height. And f of x2 is the height for the second point. I go over to the y-axis and mark that height. And since the one above is the bigger number, I put the inequality running this way. And again, we see how we can get a test out of this. Let me go ahead and write down the test, which is the algebraic definition of decreasing. So definition, again, algebraic. Same pattern as before. I want you to notice what is different here. A function, f, is decreasing. Now it's decreasing. instead of increasing, decreasing, on some interval, some generic interval, we'll just call it I, as we did before, if, again, here's the big condition, for any x1, x2 in I, again, that's exactly the same condition as before because we're moving from left to right from position x1 to position x2. x1 less than x2, that same set of positions left to right, implies this time, however, that f of x1 is greater than f of x2. Now see, if you remember the previous one, the only difference here from that previous one is that there's a greater than sign here instead of the other way. If you try and simply remember this as an algebraic definition without reference to the picture, chances are good that you will mix this up with the other condition. But if you recall the picture, you have no trouble. Here is the picture we just looked at for decreasing functions. As we move from x1 to x2, from left to right, notice that f of x1 is the higher one because you start out high and you end up low. That's what decreasing means. So there's no way possible to make a mistake here if you understand the picture. Here it's very easy to make a mistake because the only difference between this and the previous definition is the direction of this inequality. So if you connect this with a picture, you'll have a better chance of memorizing it correctly. And just to throw in a couple more decreasing pictures like I did before, here's an example of a decreasing function, decreasing. And here's another one, say like that, okay? That's decreasing. And the bend that these have, the bend down and the bend up, don't affect the fact that they are decreasing from left to right. And that's all that's of interest to me. Now, since we're on the subject of increasing and decreasing functions, what about functions that don't increase and don't decrease? Well, if they don't increase and don't decrease, it might be wise to call them constant functions. So that's exactly what we'll do. We'll call those constant functions, and they are not increasing, and they are not decreasing. So we're covering all the bases here. Constant functions. Now, what would they look like? Well, if they don't go up and they don't go down, they just stay horizontal the whole time. The graphical idea, of course, is very simple. Just doing this for completeness. Here's my axis system once again. There's x, there's y. And if this is a point C on the y-axis, then if I draw a line through that is horizontal, this would be the function f of x equals c. That says the height is always c. No matter where you go along here, you go up a distance c to get to the curve. It is constant. So if you look at a point x1 here and a point x2 here, and you try to do the same argument we did before, at x1, what are the coordinates? Coordinates are x1, c. The height is c. x2, what are the coordinates? The coordinates x2, c. The height again is c. So that is the defining property of a constant or a function that does not increase or decrease. And of course it's a horizontal line. All right. Well, among the many functions that increase and decrease or are constant, there is a classic set. One of them we just saw when we saw a constant function. That was a line. In fact, lines are sort of classic examples. So let's go ahead and toss these in now. We're going to see a lot more of lines. We've seen them already in the previous unit. Classic examples, lines. But now we'll see more of these. Let's recall, so we can put this in perspective, the equation of a line. Okay, now our favorite equation, you recall, was y equals mx plus b. That was our favorite of all the equations because the slope of the line is immediately apparent and the y-intercept is also apparent. What we're going to do is we are going to reinterpret this here as a function. We're going to rewrite the y as f of x because, as you know, we can write y equals f of x. We'll say f of x is equal to mx plus b. So this function acts on x and produces m times x plus b. The machine is the right-hand side. Well, what are the possible situations? Well, everything depends, for a line, everything depends, as far as increasing and decreasing goes, on what m is. M is the slope of the line. And in fact, we can list the three possibilities right here. Under what conditions will this line be increasing? Well, it'll be increasing for m greater than 0, because those are the slopes, the positive slopes, that make lines increase. It will be constant for m equals 0. In that case, this first term drops out and you're just left with b, f of x equal b, a constant. It's the same thing we saw in the previous picture. And then, so we had increasing and now decreasing. Decreasing for m less than 0. So with lines, we can see immediately the three different kinds of functions we just examined in general, the increasing, constant, and decreasing. Let me go ahead and show you some examples, just all on one picture. Show you that lines can illustrate all of these properties. So there are my two axes, say, and say there's a line that is increasing as I move from left to right. So its slope has, say, call this m1 for no good reason. Slope 1 must be greater than 0. Okay? So this is an increasing function. It is in particular a line. And we might have a line like this. In this case, the slope, say m2, is less than 0. This is a decreasing function. And then if I toss one in here in the middle somewhere, say there, this slope, m1, must be equal to 0, because this is a constant function. So lines illustrate all those different types of properties that functions can have, the increasing, decreasing, and constant. And now, before we leave the increasing and decreasing, let me give you a glimpse ahead to a course beyond college algebra. A glimpse ahead. And you may realize that you know more than you think you know about in calculus. In calculus, we have curves, say like that, and we look at some particular lines associated with them called tangent lines. In calculus, tangent lines are what we look at. They are the key. Hey, lines are the key in calculus. There's something you know. Tangent lines are the key to detecting increasing / decreasing. Where a function is increasing or decreasing, we will look at tangent lines to get that information. Now, we can't do that yet, but that's something that if you take calculus, you will do. And so you might say that linear thinking is good. Okay, at least in calculus it's good. And for now, however, since we don't have calculus, and we are interested in knowing where these functions are increasing and decreasing, what are we going to do? Well, here, okay, without calculus, increasing, decreasing can be hard to deduce, say, from an algebraic function. Because the definition of increasing and decreasing said for any pair x1 and x2, you had to have the property of f1, x1, and f of x2 having the relationship that they need for increasing or decreasing. So it may be difficult, depending on what the function is, to do that. However, if you have a picture, it's very easy to tell whether it's going up or going down. So, however, a graph is immediate. Okay, it's immediately apparent whether it's increasing or decreasing. So, what do? What you do is you either recognize, now there'll be some graphs that you've memorized, so you're going to recognize a function with a familiar graph, and then you can tell something about whether it's increasing or decreasing, or if it's not a function that you have any idea about, graph it with your calculator. And I mean your graphing calculator, of course. And we'll do some of that before this unit is out. In fact, let's go ahead and look at a specific case right now, just to see what this is going to look like. So here is the example I'm about to put onto the calculator. The function will be f of x equals x cubed minus 2x squared plus 3, and we'll just limit ourselves for x in the interval from -1 to 2. Okay? Now, let's suppose that you don't know anything about cubics and that you haven't got a sense of what this picture is like, and you have no idea where it's increasing or decreasing. So, I'm going to move now to the calculator, and we'll look at the picture there. All right, here's the calculator, which I will now turn on. And you may see that I've got y1 already entered in there, x cubed minus 2x squared plus 3. And what I'm going to do now is show you the window that I've chosen by hitting my window button. The window I've chosen is -1 to 2. You see the x min and x max. That's the interval we just chose. And I've chosen y min and max to be 0 and 4 because I've looked at this and I had a pretty good idea that this would be a good window. So let's go ahead and look at the graph. Here's the graph being drawn on there from left to right. And that's the cubic. It seems to go up for a while and then it goes down and then it goes up again. Now what I want to do is find out where the increasing and decreasing points, where it changes from increasing to decreasing and then from decreasing back to increasing. The easiest way to do that in your calculator is to hit the key that's marked trace. Wherever it is on your calculator, hit that key, trace. That sets up the cursor on the actual curve. Now my cursor, you see, is blinking dead center of the screen. I see that the curve is increasing at the left and seems to turn around and go decreasing about the axis, the y-axis. So I'm going to use my arrow keys here, trying not to make the screen go dark. There we go. I'm moving the cursor. There it is until I get all the way back to what looks like, well, the y-axis. And you can't read perhaps the bottom of the screen, but x equals 0 there and y is equal to 3. So I'm going to mark that down, okay? I don't care about the y value actually. I'm only really interested in the x value. So I know that that's 0. I suspected that because it looks like it's right on the axis, but I've confirmed that now. It looks like the increasing part stops there. And now let's go to the right and move the cursor all the way down to the bottom of that trough, because that seems to be the place where the decreasing, see it's decreasing where the cursor is now, where the decreasing part turns into an increasing function. So it's taking a little while to get there. Okay, I'm getting down to about where I think the bottom is. And I go until it looks like I'm roughly at the bottom, so I go back and forth a little bit. Okay, I'd say right about there is correct. It looks like x is reading 1.3333, which looks like 4/3. So I'll go ahead and jot that down. And with those 2 points, I have enough information to write down where I think the function's increasing and decreasing. So we'll move back from the calculator to the pad. Now here's the function that we were just looking at, and here's what we just learned. It looks like it is increasing approximately for x in the interval from -1, the left endpoint, to 0, and the interval from 4/3, roughly, to 2. 2 is the other endpoint. It also looked like in the middle it was decreasing. This is a little easier when you have the calculator in front of you. X in the interval then, which would be between these two, from 0 to 4/3. So now I have looked at the picture and I've seen where it's increasing and decreasing. Now this is the kind of thing with your trace on your own calculator that you're going to want to do on your own. So why don't we pause now and you can try that. Well, now that we know where functions are increasing and decreasing, you might ask the question, what happens if a function is first increasing and then decreasing, or first decreasing and then increasing? Don't we get a sort of hilly terrain? Well, that's exactly what we do get. And so now we're going to look at the ideas of local maximums and local minimums. So, local maximums and minimums, like I said, are sort of like a hilly terrain. So let me go ahead and draw an axis system here with my standard axes, okay? And let me just draw a kind of terrain here, like so. Now, if that looks like a mountain range to you, it should. That's the idea that I want to get across here. You might notice that there's a peak there. Now, it's not the highest peak, and this peak over here would qualify as that. But it certainly is a peak. And so for a certain locality, say the people living at the base of this particular peak, that would be a local maximum. So I'm going to call that a local maximum. Now we'll define this a little more carefully in a minute, but I think the visual version is the best way to start. So a local maximum is that point right there. It is also true that this point up here is a local maximum. It just has a bigger locality. And there are other local maximums in this picture. Likewise, this point here might be thought of as a local minimum, because for those living just below this little valley point, this would be the lowest point around. So locally, that would be a minimum. So we could go ahead and call this a local minimum. Now, I'm using the word local as opposed to global, and I will explain that in a minute. But a local maximum, let me go back to this first one here. How will I actually define the locality? We'd like to get very, very specific here. So imagine that right below this point is, say, a point C here. On the x-axis is right below where this maximum, this local maximum occurs. What do I mean by a locality? What I mean is simply any interval that's around C in which, if you go up to the curve, that is the highest point around. So what this is in this particular instance, this interval, you might just call it's a locality. Okay? If we come over to, say, this point over here, which is another local minimum, and we bring that down to the curve at some other point C, say, and we look at a small interval around it, then for that small interval, the graph immediately above it has this point as its local minimum. So this is yet another locality. Localities will differ, and in a different locality, different local maximums and minimums will occur. But these are clearly both local with respect to the locality. It's because if the locality were made, say, the interval that took in this entire region, then this wouldn't be a local maximum anymore. This would be the local maximum, the larger one. And the same thing goes for local minimums. So I think maybe you have a fair idea of what the picture tells us. So let's write down a couple of things to start defining these words. Definition. First of all, for us, the word local will mean the kind of thing I was conveying in the picture. Local means, say, on an interval. Since we are above, the function which represents the mountain is above the x-axis, which is the domain, on an interval, so it makes sense in this context. Now, usually it'll be a finite interval, an interval that starts and ends somewhere. But sometimes it will be an infinite interval. We'll talk about that later. Means on an interval, say, just for the record, let's go ahead and call that interval I. Now, in this course, we won't talk about global maximums and minimums, but let me tell you what they are so you'll know what the comparison is. For us, local means this, and that is as opposed to the word global. Now, as you might guess, global is like the entire globe, the entire planet, the entire region in question. Global means, well, if you're not just on an interval, then you are on the entire planet of possible x values for that function. In other words, means on the entire domain of the function. Okay? That's what global means. Now, as I said, we won't be using global in this course. Local and global become very important again when you take calculus. But local is certainly something we can understand and something we can actually look at using pictures. So let's go ahead again and look at some more pictures to fix this idea of locality and local maximums in your mind. So local maximum. Okay, let's make it really very compact. The situation is this. You have a point C on the x-axis, and above it there is a local maximum. Okay? That point is the point then C, f of C, where this is the function f of x, which I'm not writing in right now. So the height of this, of course, is f of C. That is the actual maximum value. That is the height there. Now notice that if you move away from that high point, if you go to some other point here and you measure the height is shorter than the maximum height. That's what it means to be a maximum. This is the interval I that I referred to in my definition a moment ago, if I say go from there to there. So let's go ahead and give some more words to this. F of C is the local maximum value, which is the height. Okay, that's the local maximum value. What then is C? Well, C is where that local maximum value occurs. Local max value occurs. Okay, so the second part of the ordered pair, the y value, the f of c, is the actual maximum value, the height, and the first number, the c, tells you where it occurs. Now, to give you an idea of what that means in a more interesting context, perhaps, imagine, if you will, that we are looking at the Washington Monument. There's the Washington Monument. The height of this monument, suppose the monument is positioned at C. Now, where is C? This is the location of the Washington Monument, which of course is Washington, D.C. What is then f of c in this case? Well, f of c is the height of this, and this is approximately 555 feet high. Okay, so what is this? This is the Washington Monument. It is located in the particular place, Washington, D.C., and its height is 555 feet. There is no reason to confuse those two. You don't want to confuse them when you're dealing with a function either. The value c is where the maximum occurs, and f of c is the actual maximum value. So with all of this in mind, let's go ahead and write down, finally, a definition. Definition. A function, and we'll just generically say, we'll call it y equals f of x. Remember, function f is a machine which acts on the x values which come from the domain, etc. A function y equals f of x has a local maximum at some point c. I'll put c in quotes there, and that c is in some interval I. I'll put that in parentheses. That's assumed here. If. Now, how do we tell if that point gives us a maximum? Well, as we saw in the picture, every other point nearby has a shorter value for the function. The maximum is the biggest. So, if for all x values in I, f of x, the functional value, the height at x, is less than or equal to f of c, that maximum height. Now that makes sense. That's clearly what we ought to call a maximum value. So this is called, as I said before, a local maximum value for f, the function in question. Now it's a local because there may be more than one local maximum values. It depends, as you see, on the interval, which is the locality. Okay, the interval I, let me even put that up here. This is the locality, okay, around which this local maximum occurs. All right, Well, that's a local maximum. As you might expect, local minimum is defined similarly. Let's go ahead and walk through that also, give you a chance to rethink about what we just did. Local minimum, a similar development. Okay, local minimum. Here's the situation once again. You have a point C, and right above that point C is a local minimum point. Now the coordinates of that, of course, are the same as before, C, F of C. The height here is F of C. That's what it means to be above C on the curve, F of C. The interval here we were referring to as I. Then the F of C, in a similar way that I defined things before, is now the local minimum. The local minimum value of the function, which of course again is height. Okay, but it's a short height. And the C, as before, is where that local min occurs. Okay? And as before, let me give you an illustration of that here with an actual figure. Say that is sea level. Right? Sea level. Okay, sea level. And down here below, there is a body of water. And this is the Dead Sea. Now, if you know anything about the Dead Sea, it is a sea that is below sea level. And the F of C in this case is approximately, I'll make it negative so you know it's below, minus 1,312 feet. Where is the sea? The sea, this is the location, remember, for this locality, which is the Dead Sea down here. The location of this is Israel. So the location is Israel. The actual depth is 1,312 feet downward. You'll never get these confused in this kind of situation, and so you shouldn't get C and F of C confused back here. They mean different things. C is where the local minimum occurs, and F of C is the actual height of that local minimum. Well, with that in mind, we can go ahead and do the definition just as we did for local maximum. Definition, a function, it helps to see this written out once again. A function y equals f of x has a local minimum this time, local minimum at that point C, and that's in some interval I. And that, as we said a little while ago, is a locality. That's what we mean here by I. If for all x in I, what do we want now? We want f of x, the height above x, to be bigger than or equal to the height at C. F of C is supposed to be a minimum. So there is the condition. And this, of course, is called a local minimum value for f. And again, it's a local minimum value because there may be more than one. And the reason that I went through showing you this visually is because you see the condition here. The only difference between this condition and the one for maximum is this inequality is reversed. So you have to understand what this means in your bones. And you'll understand it if you have a picture, say for minimum, like this, where that's the shortest. So if you come to any x value that's away from C, that height is bigger than f of C. That's what this means. F of x is bigger than f of C, possibly equal to f of C if x equals C, but it's always either bigger or equal to. Okay. Well, let's go back to the example we looked at a moment ago when we were looking at increasing and decreasing. Return to this example. F of x equals x cubed minus 2x squared plus 3 on the interval minus 1 to 2. And this time we want to find out where the maximum value, well, let's see. We'll find out the maximum value and where the maximum occurs. right? So the maximum value will be what we've been previously calling f of c, and c will be where the maximum value occurs, and do the same thing for minimum value. So minimum, set things up here. So I'll just fill in the blanks when I go to the picture. This will be f of, okay, since we're using c, let's call this c1, call this c2, just to keep them different, and then where the minimum occurs. Okay, the actual location of that. Okay, we'll come back to this. Now let's go to the graph on the calculator and see exactly what this is going to look like. So here's the calculator once again. Turn it on. There's the graph as it was before. You see the cursor blinking in the middle of the screen. And now I'm going to show you another feature that this calculator has, and most calculators have as standard. There is a way to get immediately to the max and the min. Now you can see where they are by looking at the picture. There's that high point at the y-axis and then that low point on the right. But instead of just guessing by moving trace, there is yet another way to do that. And on my calculator, I have to go ahead and go to, let's see, calc, which you see is right above trace. That's a second function. So I'll hit my second function and then calc, and I get a little menu. Now in other calculators, the menu will be similar. You'll notice that if I go to the right and then come on down, you'll see there's a word that says minimum. There's a word that says maximum. Okay, what the calculator will do if I enter one of these, as I will do now, say I've got maximum highlighted, I will enter that. It will say calculating or some other message like that. And what it is doing is it is looking at all the pixels representing the graph, and it's going to find the one with the biggest y value. Now it's finished, and you may see that the cursor is blinking at the very top of the screen up there. And that is indeed the maximum. And if you read, although it may be difficult for you to read, you may see that the x is 0, of course, and the y value is 3. So I'm going to write that down on my paper here. The x is 0, that's the position, and the height is 3. Then if I go back to the same thing as I did before, the calc, which will be different on your calculator perhaps, but there's a menu there somewhere. And I go over there and I pick up minimum this time, and I hit enter. It again says calculating, and it's going to go to the minimum, the smallest value. Now let's see what happens. You know where you want it to go. You want it to go here, and it did go there. Okay, because that was the nearest minimum. You may notice that the left side of the screen, the curve goes down below that. Okay, let me move that out of there. All right, let's read that off the screen. Again, it's 4/3 for the x, we saw that before, and about 1.81 for the y. So about 4/3 for the x and 1.81 for the y value. Okay, having written that down, I can go back to my pad. And you see I have written down here the numbers that we got off the calculator. These are the kind of calculations that you will do with your calculator. And so I have an idea where the maximum and the minimum occur, and I have an idea of what those values are. Now, you might say these are not exact. Well, maybe they're not exact, but we can't make them exact without calculus, which we won't have in this course. But we can do quite a good job with the calculator. And so, having seen that, it's time for you to try this on your own. Practice a little bit with your calculator and try and look for some maximums and minimums on a few curves that will be given to you as examples. So we'll stop there and we'll go on in a moment. We're continuing to look at functions graphically, trying to see how from their algebraic formulation we can learn something about their graphs, and from their graphs learn something about the algebra. Now we're going to look at something which has a rather odd description, it may seem, even and odd functions. What could that possibly mean? We know what even and odd numbers are, but what are even and odd functions? Well, what this will bring back from the previous unit is the notions of symmetry of graphs that will allow us to graph things a little more easily. So let's go ahead and first look at even functions. And for even functions, let me do a little motivation. At least I hope it'll be motivation. Motivation here. Observe the following situation. Okay? Let's look at a very simple function, say f of x equals x squared. Now that's an even power. All right. Now let's examine, say, f of 3. If you put 3 into the function f of x equals x squared, of course you get 3 squared out, which is 9. Let us also put in f of minus 3. So we're putting minus 3 into the box and squaring it. Notice that the parentheses are necessary here because this is really a box. The x is a box, and I'm putting minus 3 in there. Minus 3 squared, of course, as you know, also gives you 9. These are the same. And please note that this power is even. Okay, let me do another example. Also, let's look at, say, g of x equals maybe x to the 4th minus x squared. And then let's look at, say, g of 2. Well, that's easy enough. That's 2 to the 4th minus 2 squared. And 2 to the 4th is 16. 2 squared is 4. So this is 12. Let us also look at g of minus 2. Now remember, this is g of box equals box to the 4th minus box squared. I'm now going to fill the box with minus 2. So I have to again be careful with my parentheses. Minus 2 to the 4th minus minus 2 squared. See, there's already a minus here, so we do have to be careful. Well, minus 2 to the 4th is the same thing as 2 to the 4th. And minus 2 squared is the same thing as 2 squared. So I end up with the same result, 12. Again, these are the same. And please note that all the powers involved here are even. Well, with all of that as a hint, let's come up with a definition for what an even function is. From these hints, we will make the following definition. We will say, and this is an algebraic definition, let me go ahead and write this down. We will connect this up to a picture, the graphical picture soon. The algebraic definition is a function f is even if, well, let's see, what happened? When we put in 2 or minus 2 or 3 or minus 3, we ended up with the same result. Another way to say that in general is that if I take f of minus x, I always get the same thing as f of x. Now that is the condition, and that will have to work for all x and minus x in the domain of f. I will make that my definition of what it means for a function to be even. And you can see why it's called even, because it's just like even powers. But let me caution you that not all functions that are even are just even powers. In fact, there are some trigonometric functions which are even. So evenness is a property that actually extends beyond its genesis from even powers. All right, this was the algebraic definition. Let's see how this would mean, what this would mean graphically. So definition, graphical. Everything you do in algebra, try and get a picture of. Sometimes you can, and sometimes you can't. But most of the time when you can, it's enlightening. All right, let me draw a couple of axes here, my x and my y axis. And even means, let me put the condition up here, f of minus x is equal to f of x, just to remind me. Well, that means if x is a point over here, and minus x, say, is a point over here, then the functional value, which is the height, is the same for both functions. This is x, f of x, and this point is minus x, f of minus x, but f of minus x is the same as f of x. So these 2 points are the same. The height, I'm sorry, the points are not the same, the height of the points is the same. So that is what it means to be, graphically, to be even. Well, what does that mean? That means for every point here on the right of the y-axis, there is a corresponding point on the left of the x-axis. In other words, we have symmetry across this axis, which acts like a mirror. Okay, the mirror is the y-axis, which is a line. So you can imagine yourself over here looking into the mirror and seeing your reflection over here at the other point. Now we had a name for that. We saw in the previous unit that we call this the graph of an even function. Graph of an even function is, what did we say? We said symmetric. Symmetric about or around the y-axis. It has that mirror symmetry back and forth, which means you only have to graph one side and you know what the other side looks like. So you want to recall this, okay, from the previous unit. All right, well, graphically that's great. Let's see what a couple of these even functions look like. Fix this picture a little bit more in our minds here. Here's an example, a couple of pictures. First one, let's look at the function f of x equals x squared. These two functions that I looked at. First, the x squared function. What does the graph of that look like? Well, if you graph it on your calculator, or you may already know from your previous knowledge, it is a graph that looks like that. It is what's called a parabola. We'll deal with that name a little later. And you can see that it is symmetric from left to right. And, of course, it's x squared. It's the classic even function. Let's look at g of x, that other function we looked at, which was x to the fourth minus x squared. If you look at the graph of this, and I did this on my graphing calculator to see what it looked like, it looks like this. If I can draw that more or less symmetrically, it is symmetric from left to right. Okay, it's got this little bump in the middle, but that's certainly symmetry from left to right. And if this is x and this is y, it looks like the other graph now. So there you have it. Even functions are symmetric around the y-axis. Great. Now we just need to come up with a definition for odd functions. Well, based on what we've done, we've got a path to follow. So, odd functions. How would we define odd functions? Well, we'll work with the same kind of hints as before. Similarly, observe the following. I'll give you two examples here also. Suppose we have a function, say, h of x. I'm going to start varying the names of functions so you get used to that. I don't want to use f of x all the time. Let's say h of x is x cubed. Now notice that that is an odd power. Let's then look at h of 3. Well, h of 3, of course, is 3 cubed. 3 cubed, you should know, is 27. Let's also look at h of minus 3. Now this is h of box equals box cubed. So whatever I put in for x, I must put in for x here and cube it. Here I'm putting in minus 3. So again, I want to carefully use parentheses and write minus 3 cubed. But the thing about odd powers is the negative sign is preserved because this is minus 1 in here cubed, and minus 1 cubed is minus 1. And then the 3 cubed is 27, so we end up with minus 27. Now we see that this number is the negative of that number, and please note that the power is odd. Let me look at a second example. Say this one. Likewise, let's look at, say, how about p of x? Another letter, x to the fifth minus x. So there's the function we're going to look at here. Let's look at p of 2. Say. Well, that's 2 to the fifth minus 2. Now 2 to the fifth, you may know, is 32. 32 minus 2 then is 30. Then let's look at p of minus 2. Now again, that's a negative, and I want to preserve it carefully with negative signs, with parentheses rather. So negative 2 to the fifth minus negative 2 in parentheses. See, with the minus in the problem, it's especially important that you use your parentheses well. Well, minus 2 to the fifth, again, the minus is preserved by the odd power. So this, instead of being 32, is negative 32. And then we're adding, since minus minus, 2. So negative 32 plus 2, negative 32 plus 2 is negative 30. Again, this is the negative of the previous one. And notice that the powers here, both cases, the powers are odd. Well, from these hints, let's see if we can write down a definition that is similar to the one for even functions. So from these hints, let's write down the following very simple definition. And again, this is an algebraic definition. We want to do a graphical version of this to see what kind of symmetry, if any, this means. Let's see. A function f is what we'll now call odd if f of minus x did not give us back f of x, that would be even, but gave us back the negative of the original. So it gave us back negative f of x. And that would have, in this case, we would want this to work for all x and minus x in the domain of f. F of minus x equals minus f of x. What is this like? Well, of course, this is just like odd power functions. Now let me caution you again that not all functions that are odd, in this sense, are power functions that are odd. For example, there are trig functions, just as there are for even trig functions, that are in fact odd. But this is where the idea came from, and this is where the name comes from. Let me now we've looked at algebraic, once again let's look at the graphical version. So definition, this will be graphical. And in the graphical version, we would hope that similar to the even function case, there is some sort of symmetry going on here. So let me go ahead and draw a little picture here, my axes x and y. And remember what the condition was here, f of minus x equals minus f of x. I'll put that up here in the corner to remind me. Okay, so that means if I mark off an x point and a minus x point here, let's see what would happen. X, of course, goes to whatever height it goes to. X goes to f of x height. Okay, so this is f of x height. Now where does minus x go? It goes to the negative of that f of x height. So instead of going this distance upward, it goes that distance downward. This is negative f of x. So this point here will be minus x comma f of minus x, but f of minus x is minus f of x here. So it goes down to this point, which is the same distance that this went up, except it goes down. So what we have here, if you remember from the previous unit, is we have symmetry across this point. Now this is a little unusual. It's not line symmetry like the mirror that you see, but the mirror here equals the point 0, 0, a point instead of a line. And we have symmetry across there. So any point that appears up here, xf of x, you simply negate both of the terms, both of the coordinates in the ordered pair, and you end up with a point that is corresponding to it across the origin. And that's symmetry with respect to the origin. So let's write that down. The graph of an odd function, in the definition we've used, an odd function is symmetric with respect to the origin. And the origin, of course, is the point 0, 0. Now that's a symmetry we examined in the previous unit. So this is something you've seen before, and now we know how to interpret this in the language of functions. If a function's odd, it's symmetric with respect to the origin. If it's even, it's symmetric with respect to the y-axis. Now before we leave odd functions, let me go ahead and give you a couple of pictures here, just as I did before. Example. Here the first one we looked at was h of x equals x cubed. This is one of those functions you're going to have to memorize, so it doesn't hurt to see it several times. And the function looks like that, more or less. And you see it has that symmetry running across the origin. For every point over on the left, there's a corresponding point across the origin. And the other function, which was p of x equals x to the fifth minus x, looks a little bit like this. There's my x and y axes. It comes up, goes down, and goes up again like that. And of course you can see the symmetry is working here also. If you have a point here, there is a corresponding point on the other side. Also, if you have a point here, a corresponding point on the other side. Through the origin there is symmetry. Okay, well now we have even defined and we have odd function defined. The natural next question is, well, it's first of all to remember something. Remember, in the natural numbers, very first number set we ever looked at, 1, 2, 3, 4, etc. out to infinity, every number in there is either even or odd. In that number set, all numbers are either even or odd. Okay? 1, 3, 5, etc. are odd, 2, 4, 6 are even. That's what mathematicians would call an exhaustive classification. Everything is covered by these two descriptives. Well, once you have that and you've defined even and odd functions, the natural question is to say, are all functions either even or odd? Answer. Well, if you stop to think about that for a moment and think about it graphically, remember, if they were all even or odd, then the graph of every function would either be symmetric with respect to the y-axis, which would be an even function, or symmetric with respect to the origin, which would be an odd function. Now, you know there are functions that are not symmetric in either sense, so you probably know that the answer is no. But if I'm going to convince you mathematically, I should give you a counterexample. I should provide you with a function that is neither even nor odd. So let me give you a counterexample. Okay, counterexample, the function is f of x equals x plus 1. Very simple function. And let me prove to you that it is not even and it's not odd. Let me just do it by example. F of minus 3 is equal to minus 3 plus 1. I'm just substituting in for x here. And of course, that's minus 2. F of 3 would be 3 plus 1, and that, of course, is 4. But please note about these that f of minus 3 is not equal to f of 3, because minus 2 is certainly not equal to 4, so that means the function is not even, because this has to hold true if it's an even function for all numbers in the domain. Also, and say, f of minus 3 is not equal to the negative of f of 3. Now what exactly is that? F of minus 3 is minus 2, and I'm claiming that's not equal to negative of f of 3, which is negative 4. Clearly that's true. So we have not even here, and this shows it's not odd. Because in odd functions, f of the negative of a number is negative f of the number. So if it's not even and it's not odd, it must be, of course, neither. And there's a perfect example, very simple function that's neither even nor odd. So not all functions are even or odd. And as I said, it's because there's no symmetry here in either of the two senses. Let's graph that function just to finish off the example. Graphically, say, comma, this means what? Well, here is the graph of this function. There's x and there's y. The function x plus 1, f of x equals x plus 1 is a very easy function to graph. We'll talk more about this at another time. But the function looks more or less like this, passing through 1 here and minus 1 here. Now you can see that it's not symmetric across the y-axis because there's a point here, but there's no corresponding point here. It's also not symmetric across the origin because if I take this point and I go through the origin, there's no corresponding point down here. So it's symmetric in neither sense. And so not symmetric that way or not symmetric that way. So it's symmetric in neither sense, and it's neither even nor odd. So that's just an example to show you that when you're looking for even and oddness, not all functions will have that property, one of those two properties. So if you find one that doesn't, just move on. All right, I think it's time for you to practice that a bit, and I'll be back.